The goal of the symposium is to celebrate the hard work of our Polygence scholars, all of whom have tirelessly worked on their projects over the past couple of months. My name is Ojasvi Mudda, and I am the Chief of Staff here at Polygence, and I'm also a recent graduate of Yale University. Today, we have a full roster of amazing projects to share with you. We have 5 student presenters presenting on a variety of topics. In the room today with us is Judge Andrew Smith. Andrew is a PhD student at Wharton's marketing department, focused on interpersonal dynamics. He will be scoring each student presentations along with myself. Please type your questions in the chat if you have any for each speaker. We will allot 2 minutes for questions after each presentation. I will hop back in the room again with 2 minutes remaining. So that will be the agenda for today. So first up is Anya, a sophomore from Foster City, California. Anya, if you're ready, feel free to text me and I will share screen. Amazing. Hi, Anya.
Hi.
The stage is yours.
So how do I share my screen?
Sure. So do you see a button? There's like one button for video, one for audio, and the fourth one is screen sharing. Do you see that?
Oh, yeah.
Perfect.
Thank you.
Of course.
All right. My Polygence project is on amyloid-beta in Alzheimer's disease, the way it contributes to the progression of the disease, and recent clinical trials addressing this. To start off, if you can all think to yourselves, which of the following best describes the picture at the right? So at this point, I'm sure a lot of you are a little confused. And try to imagine this is a daily activity of yours, something you've done millions of times before. And you're probably struggling with it at this point. You would probably feel stressed and frustrated and a little paranoid. So this was an exercise developed by researchers to emulate what patients with Alzheimer's disease feel on a daily basis. So what causes people to experience this? Alzheimer's disease is a progressive neurodegenerative disease, which means that its symptoms occur in a cascade of worsening. It's been associated with memory loss and other cognitive deficits for which there's currently no cure. As of right now, 6.2 million Americans are affected by this disease, and that number is projected to grow to 13.8 million Americans by 2060. As of right now, the US government spends about $355 billion on this disease alone. It is a huge economic burden, a huge burden on the families of people who have to deal with this disease, and it is something that needs to be addressed. So it can be split up into 4 broad stages. Preclinical AD, in which the pathologies may be present but no symptoms show yet. In mild AD, symptoms such as memory lapses and difficulty in concentrating begin to show. In moderate AD, symptoms escalate to significant memory loss and difficulty in completing daily tasks. And finally, this culminates in severe AD, with an entire loss of physical capability, an inability to hold a conversation, and loss of brain function that can eventually lead to death. So first, this disease affects the hippocampus, which is in charge of memory formation and spatial learning. This in turn causes the memory lapses that you see in mild AD. The typical demographic affected first would be people aged 65 to 80 years old. And while this is when symptoms begin to show, the pathologies can be present as early as 20 years before. So how does A-beta, the focus of my project, contribute to the pathogenesis of this disease? Amyloid-beta or A-beta is a short neurotoxic protein fragment. What this means is there is a protein in the brain, amyloid precursor protein, which is vital for the development of neurons. However, in Alzheimer's disease, it is cleaved by 2 enzymes, gamma secretase and beta secretase. And this means they kind of go in like scissors and they snip the protein in half. And this leads to these green protein fragments seen at the right. These protein fragments are A-beta and they're highly neurotoxic in Alzheimer's disease. They misfold and kind of clump together in these sticky things known as amyloid beta plaques. These plaques are insoluble aggregates of these misfolded proteins, and they can disrupt neuronal transmissions, the way neurons communicate with each other and send signals to one another in order to help form new memories. This is why memory loss is caused. Alzheimer's disease is thought to partially result from the abnormal cleavage of this protein and the overproduction of A-beta peptides. So here shown is an A-beta plaque as it interacts with the neuron to obstruct the way it can send signals to other neurons. This in turn causes neurodegeneration or a cascade of worsening symptoms and cognitive impairment seen in Alzheimer's disease. So currently, what are researchers doing to address this disease? What drugs are on the market to help cure this disease? The stages of a clinical trial can be split up into three main categories. Preclinical studies, which are typically lab studies done in mice to observe the way a drug, if it works, how it impacts these mice, and if it does well in preclinical studies, it can move on to phase 1 and 2 of clinical trials done in humans. In these clinical trials, it is typically tested in phase 1 and 2 on human safety and tolerability. If it is shown to react well with the body in these two phases, it moves on to phase 3 testing, in which researchers take a randomized population where the sample size is much greater and it is double-blind, placebo-controlled, and they test how effective the drug is. So currently there are many therapeutic interventions targeting A-beta under investigation. However, historically, there's not been much success seen in these trials. It has highly been posited that this is because intervention simply occurs too late in the disease process. However, monoclonal antibodies are a very promising future prospect and are currently one of the most promising types of drugs that target A-beta and slow the progression of Alzheimer's disease. They are intravenously infused and entail the direct infusion of antibodies that target A-beta. So aducanumab is a monoclonal antibody, or mAb, that selectively targets A-beta aggregates. On June 7th of this year, the FDA actually approved aducanumab for treatment. This is very controversial because it is the first approval of an Alzheimer's disease drug in the first 18 years now. And they argue that there's not enough data to establish efficacy or statistical significance, and many researchers are very skeptical of this drug. This is because of the two results of the two phase 3 trials. In one phase 3 trial, ENGAGE, there were no statistically significant differences found in cognition of the patients, and neither the primary nor secondary clinical endpoints had been met. In the EMERGE trial, aducanumab significantly reduced A-beta plaque load, and cognitive decline was reduced by up to 22%. Because of these inconsistent trials, many researchers are doubtful of the new approval and worry that it may not work and instill a sense of false hope in patients. Another mAb is donanemab, which targets one specific end of an A-beta peptide. It has not been approved yet as it is still undergoing its phase 3 testing, but in one study, it decreased brain A-beta load by up to 50%. In another recent clinical trial, it reduced cognitive decline, which is very unique because typically anti-A-beta drugs often reduce the amount of A-beta in the brain, but never actually slow cognitive decline or improve the symptoms of Alzheimer's disease. In addition, donanemab has a high potency, which means only a low dosage of the drug is needed to yield significant results. This is once again very unique to donanemab because typically with Alzheimer's disease drugs, the dosage needs to actually increase throughout the trial to see significant results. This is good because it can prevent excessive side effects and save money and resources if only a low dosage is needed to see results. However, donanemab has been associated with brain volume loss. So in one trial, brain volume loss was significantly higher in donanemab-treated subjects than in placebo groups. Future trials, in my opinion, must evaluate and enhance its safety in regards to serious side effects and adverse events, and better analyze this correlation. So in the future, I think we need to address the low efficacy and marginal cognitive improvement historically seen in these clinical trials. I believe we can do so by intervening earlier on in the disease process. I also believe donanemab is currently the most promising up-and-coming drug on the market, and in the future, we need to conduct more trials to elucidate any adverse side effects. In addition, we need to consider how the recent controversial approval of aducanumab will change future trials. For example, patients may be hesitant to enroll in other trials for other drugs in the future because there's already a drug on the market that they may think will cure them. We also need to be sympathetic, most importantly, and supportive to the families of people who have to deal with this disease. So thank you for your attention, everyone, and I'd love to take any questions now.
Thank you, Anya. That was amazing. I definitely learned a lot from your research process. Yes. So audience, feel free to ask a question in the chat room or like asking the Q&A box, and I will ask on your behalf. And while we wait, I actually have a question for you. So I'm just curious, were there any roadblocks with your research process? And what are like roadblocks? Like what are like the biggest challenges?
So yeah, the greatest challenge would be intervening earlier on, simply because diagnosing and screening for biomarkers is a very strenuous and expensive process. So I believe that if we were to invest more time, money, and resources into better screening opportunities, looking for biomarkers such as the presence of A-beta or the presence of other such indications of the risk of Alzheimer's disease, then we can really intervene earlier on and prevent this disease from progressing.
Got it. And what are some things that we can do, so young adults and students, to help with this very big issue when we are not like researchers or not necessarily in the field? If you have any recommendations?
Right. I think just educating ourselves, doing our research, trying to understand, instead of just seeing the headline, new Alzheimer's disease drug approved, actually reading about it and learning, oh, this may actually be false hope because the results of the two trials were contradictory. And just educating ourselves and best supporting people we see around us if they have to deal with this. Oh, I think you're muted. For me, you're still muted.
Okay.
Oh, now I can hear you.
Great. I was trying to invite Finlay to the stage, but I think I might have lost Finlay. But I will ask for Finlay. So what was the most surprising fact that you learned in your research? And hi, Finlay. He's here.
The most surprising fact was definitely how much money we invest per year, $355 billion. It is the greatest healthcare expenditure of the US government. And I didn't realize that we spend so much, even as much as cancer research, and we still haven't found a cure.
Finlay, feel free to throw additional questions.
That's really surprising, and I really enjoyed your presentation. One more question. How did you approach finding all this information on Alzheimer's?
I think PubMed is a great resource in general for finding papers and the most recent literature on a field. So a lot of times I would look up keywords on PubMed, Alzheimer's disease, A-beta, and just read a lot of the up-to-date research.
Awesome, thank you.
We also have another question from the audience. What is the success rate of the present drug?
The present drug in clinical and significantly A-beta load, although I don't have that number on me right now.
Got it. Thank you so much.
Thank you.
All right. Yeah, thank you, Anya. And next up, Finlay, do you mind request share again so I can bring you up to the stage to give your presentation? All right. He is coming. Yes. So yeah, so second, we have Finlay, a senior from Santa Barbara, California. Take it away. Finlay, let me know if you need any help with pulling up your presentation.
Yeah, I'm just trying to figure out how to share my slides.
Yeah, so there's a button on the bottom with like a monitor symbol. Do you see that? Is the fourth one.
Should I select window?
Either way works if you have your presentation in a separate tab. Yeah, you might have shared your entire window. Oh yeah, perfect. We see it.
I see. Okay.
Great.
Can you see it?
Yes.
Amazing.
Um,
All right. Good morning, everyone. My name is Finlay Hastings, and I'll be presenting Oh, the Places You Won't Go, a comparative analysis of tropical disease, culture-bound syndromes, and genetic disorders. Oh, the Places You Won't Go is a comparative study in the field of epidemiology. So this presentation will bring to light novel relationships between seemingly unique and independent disease categories to possibly uncover comparative solutions to widespread occurrences of disease. Many of you may be familiar with the children's poem, Oh, the Places You'll Go by Dr. Seuss. This story teaches us to travel to places unknown and truly find an appreciation for where we end up and the places that we call home. I believe that this message serves a unique role in the study of epidemiology, one that pushes us to understand the diseases that we may be exposed to through a geographic lens. Tropical disease, culture-bound syndromes, and genetic disorders affect a large percentage of the world population today. And in my presentation, I'll focus on 6 of the 9 diseases that you see on the screen in 3 different distinct categories and their geospecificity related to who they affect and how they're transmitted. My research consisted of compiling available resources and literature on specific contagious diseases and creating my own interpretation of existing findings. I found that there are many steps to addressing disease and that the path to a cure is long and often complex. Tropical diseases like malaria and schistosomiasis together infect hundreds of millions of people every year. They plague the tropical and subtropical regions of the world, namely equatorial areas. And malaria is transmitted via mosquitoes, and schistosomiasis can be contracted through freshwater parasites. Culture-bound syndromes are identified as psychosomatic illnesses due to their transmission through human interactions. Hwabyong, which loosely translates to anger illness, is known to Korean culture, Korean women in particular. Their susceptibility to domestic abuse and cultural hierarchies often force patients to suppress their emotions, and that can lead to possible contraction. Susto and Karahe, illnesses that impact the Amuzgos Indians and Mexicans in Latin America, share similar anger and anxiety-induced illnesses and symptoms as Hwabyong. Eating disorders have taken root in many cultures around the world, and I studied their impact on westernized cultures, such as those of North America and Japan. Culture-bound syndromes can manifest in any specific cultural environment and are presented through physical symptoms, which is why I included them in my research. Lastly, genetic disease Tay-Sachs can adversely affect the Ashkenazi Jewish populations of Eastern and Central Europe. This disease is prevalent in this demographic because of the close and oftentimes shared family lineage within these communities. I identified tropical disease, culture-bound syndromes, and genetic disorders as representative illnesses of disease as a whole. Surprisingly, I came across specific similarities between these diseases that led to possible combative solutions. So, how are geographic, demographic, and transmission similarities signals of a common preventative solution? Well, there are countless differences between these seemingly unrelated illnesses, but what is truly fascinating are the similarities. The following slides, I will examine some of these cross-category comparisons. Small-scale interactions. Dormant diseases are those that do not, Small-scale interactions. Diseases affect different demographics and population sizes, both big and small. I found that Tay-Sachs and Susto and Karahe thrive in tightly knit communities, often with close familial ties. Due to the constant and inevitable interactions within these distinct communities, disease spreads easily and has taken root as a result. So how can this similarity bring to light a solution? Case studies around the Amuzgos Indians and their experiences with Susto and Karahe showed lower rates of anger-induced mental illness when family units were mindful of lowering their voice and suppressing their negative emotions in the household. This helped to eliminate the contagion and move in the direction of a cure in the community. Given the similarity in size of the impacted demographic, it makes sense that ensuring awareness in Ashkenazi Jewish populations could also act as a solution. In analyzing how Tay-Sachs and Susto and Karahe have impacted smaller communities, it becomes apparent that communal awareness of the diseases that they are susceptible to can be preventative. When these impacted demographics fully understand how the diseases they face remain pervasive, communal change can be set in motion to further deter sickness. The dormant disease. Dormant diseases are those that do not present symptoms recently after contracting the disease. So how is it that this unique property of some diseases exists in both tropical disease and culture-bound syndromes? Huabiang is a dormant disease in that susceptibility largely relies on interactions with usually male counterparts. And these interactions can span entire lifetimes and are often linked with domestic abuse through one's cultural experience. This stunning fact shows how culture-bound syndromes follow culture and not always location. Similarly, malaria can also remain dormant in our bodies and appear later even after we've left an area of susceptibility. This can be months and even years. Just like Huabiang, leaving the place of origin for malaria doesn't mean that you've evaded the illness. In understanding that the environments that we expose ourselves to, both geographical and cultural, we can hope to identify dormant diseases like malaria and Huabiang sooner and provide more effective treatments. Testing the waters. The consequences of untested water and exposure to social media and cultural pressure is similar in its unregulated nature. These diseases do not share regional proximity, but are transmitted similarly to unaware patients. Testing the waters is a saying that can be used both literally and figuratively in the context of these two diseases. In the literal sense, interacting with fresh water in tropical regions may leave you susceptible to contact with a schistosomiasis-causing parasite. It is important that when visiting known tropical disease regions, the traveler is prepared and cautious of the vectors that they might be exposed to. In the figurative meaning, to test the waters is to be vigilant and to take an experience slowly, as in getting your feet wet. There are almost 4.5 billion social media users in the world, making susceptibility to mental illnesses associated with media use, like eating disorders, highly pervasive. There's no solution in completely eliminating things that are part of our everyday lives, like traveling and using social media. So testing the waters serves as an anthem to be more aware, while continuing to experience the very things that define our everyday lives. Appreciating your wake in an environment, whether it be a tropical or virtual one, can help prevent the contraction of stealth diseases like schistosomiasis and eating disorders. So what do these comparisons mean and what do they tell us about disease? With the help of Oh, the Places You'll Go, I came to the conclusion that building awareness and understanding of the environments and diseases we are exposed to can help in many cases. These illnesses may seem incurable, but can be avoided through knowledge of the environment. Oh, the Places You Won't Go showed me that largely puzzling issues, such as global illness, can become approachable through comparative analysis, and these novel connections provide an understanding of the entire scope of diseases that could possibly harm us. You have brains in your head, you have feet in your shoes. You can steer yourself in any direction you choose. The first step to addressing most global phenomena parallels that of Dr. Seuss's message, to gain an appreciation of where you are, good or bad, home or foreign, and to find the ways in which we can preserve our health. Thank you so much for listening.
Thank you. That was great. So actually, Finlay, come back. We still have time for Q&A. So if you have any questions, please feel free to put in the Q&A chat box, and I'll ask for you. Yeah, Finlay, do you mind request share video and audio again, so I can bring you back up? Perfect. It's coming.
Hi, sorry about that. I got out of the meeting.
No worries. So audience, if you have any questions, please feel free to text, and I will ask on your behalf. Well, we wait. I think it's very important that we really focus on the right way of doing community building. As you mentioned, there's a lot of problems, when people live in close-knit quarters. So what would be the one takeaway that you will have for the audience to keep in mind for future community building, especially from the frustrations or something like you heard from your research?
Yeah, that's a great question. And the main point that I identified in my research has to do with that problem exactly. And it's what is the first step that we can take to address disease, but more generally, how can we address any issue that we may come across, whether it be a communal challenge or global disease in general. And that is just gaining an awareness of where we are and our environment and the different vectors that we may be exposed to. And I found this through the literature analysis, comparing my project to the Dr. Seuss poem.
Yeah, got it. That's cool. And I think I want to ask the question you asked Anya earlier. What was the most surprising fact that you learned from your research?
So I went into this research project completely open to any sort of diseases that came my way and that were very interesting to me. And I found that these very unique categories, culture-bound syndromes, tropical diseases, genetic disorders, have a lot in common if you really break them down in a geographical sense. So which demographics are they impacting, who they're impacting, where. There's a lot of similarities that you can pull out from those. And then through that, I found those common solutions, which I found was very surprising and interesting.
Yeah, that is very surprising. Yeah, well, thank you so much. Like our audience said, that was great. So thank you so much. And next up, I'm going to invite Sophia to stage. So Sophia, welcome. Sophia is a senior from Bellevue, Washington. Take it away. And also let me know if you need help with setting up your presentation.
Okay. Let's see, can you see my screen?
Okay. Yeah, perfect.
Okay, great, thank you. All right, hello everyone. My name is Sophia Dettweiler, and I'm excited to be sharing with you today my Polygence project, which is titled Factors Associated with Atypical Presentations of Alzheimer's Disease. So before we start talking about my project itself, I'd like to give you some background on Alzheimer's disease and normal aging. So first of all, it is completely normal to experience some cognitive decline in aging. However, once this goes beyond the normal amount, it could be considered mild cognitive decline, or MCI. Individuals with MCI typically require help with some tasks, but it generally doesn't interfere too much with most of everyday life. MCI sometimes, but not always, progresses to become dementia, which refers to a variety of clinical symptoms which vary based on the type of dementia, from memory to language to behavioral problems and more. Dementia usually does severely affect daily life and requires assistance for many everyday tasks. Dementia can be caused by various neurodegenerative diseases, including Alzheimer's disease, or AD. Dementia that is believed to be caused by AD is called Alzheimer's dementia, or dementia of the Alzheimer's type, sometimes called DAT. Though these two terms, Alzheimer's disease and Alzheimer's dementia, are often used interchangeably, it's very important to distinguish between the two. Alzheimer's disease refers to a neurodegenerative pathology, so what is physically happening in the brain, while Alzheimer's dementia refers to the clinical syndrome, or the symptoms that are observed. AD is caused by two types of proteins that misfold, clump together, and accumulate in the brain. These two types of aggregates are amyloid-beta plaques, like Anya talked about earlier, which are found outside of neurons and are shown in brown on the image, and neurofibrillary or tau tangles, which are found inside of neurons and are shown in red. These plaques and tangles disrupt synapses, prevent neurons from functioning correctly, and eventually cause neurons to die, which leads to major atrophy in the brain. Plaques and tangles are also associated with low glucose metabolism and microglial activation, which also contributes to disease progression. What makes the study of dementia syndromes and the underlying diseases that cause them even more complex is that the same neurodegenerative disease can also lead to very different clinical symptoms. So the typical presentation of AD is Alzheimer's dementia, or DAT, which initially primarily causes memory impairment and then leads to cognitive decline in other areas. This is typically what people are referring to when they just say Alzheimer's. However, AD also has several atypical presentations with their own distinct patterns of pathology and symptoms. For example, AD can also cause primary progressive aphasia, or PPA, which is characterized by language dysfunction. AD is specifically associated with a logopenic subtype of PPA, which causes difficulties with word retrieval. Finally, superagers are individuals over the age of 80 who have vastly superior cognition for their age. Specifically, they have memory abilities similar to people in their 50s and 60s. Many superagers do have lower than average levels of AD pathology in their brains, as you might expect, but surprisingly, some have significant levels of AD pathology present. These superagers who do have AD pathology present but don't show any dementia symptoms and instead even show superior cognition could be considered another atypical presentation of AD. And this was the main focus of my project, to learn about what factors are associated with DAT, PPA, and superaging to better understand why and how AD leads to these different presentations. So now let's break down the pathology for each of these different presentations. First of all, the location of the pathology generally relates to the symptoms it causes. So for example, DAT starts in memory areas shown with the blue X's in the lower image. And since the pathology is in memory areas, that causes memory decline. And then the pathology spreads symmetrically across the brain, which causes the more general cognitive decline seen later in the disease. Similarly, in PPA, AD pathology starts in language areas represented by the red X and is much more severe in the language-dominant hemisphere, which is usually the left. Compared to normally aging individuals, superagers often have significantly fewer tangles, as you can see here, but similar levels of plaques, which supports the conclusion that tangles are more strongly associated with cognitive symptoms than plaques are. Now I'm going to talk about the factors that are associated with each presentation, but I do want to give a quick disclaimer that none of these factors single-handedly cause AD or any of these presentations. They only increase or decrease one's risk. So let's start with factors associated with Alzheimer's dementia. Some factors that may increase risk are older age, which is the single largest risk factor, being female, having a certain risk increasing version of the APOE gene, which has been strongly linked to one's risk of developing AD, a family history of AD, a personal history of MCI, and cardiovascular disease and associated factors. Some factors that may decrease risk are a generally heart-healthy lifestyle and a mentally stimulating life, including social life, education, and career, as well as higher socioeconomic status. Primary progressive aphasia generally has a younger age of onset compared to Alzheimer's dementia, typically before age 65, so older age is not as much of a risk factor compared to DAT. Interestingly, the APOE4 allele, which is a major risk factor for Alzheimer's dementia, appears not to be a risk factor for PPA. A history of language learning disability and brain damage to the left hemisphere are both associated with PPA, and this may be because these factors weaken the language areas and make them more vulnerable to AD pathology. More research is still needed on lifestyle and other factors that may protect against developing PPA. Now some factors associated with superaging. Superagers are more likely to be female, with good overall physical health, extroverted personalities, and cognitively stimulating careers and leisure activities. Interestingly, superagers actually have normal IQs on average, and they display normal distributions of the APOE alleles, meaning that that specific gene doesn't necessarily protect them from developing AD. Some superagers follow an extremely healthy lifestyle, while others don't at all, so it's still very unclear how much lifestyle is a factor in superaging compared to biology and other factors, so this is a crucial area of future research. I identified three main future directions related to this topic. First, general further research could provide valuable insight into the causes of AD and its different clinical presentations, and even potentially prevention and treatment methods. Some gaps in current knowledge that could benefit from further research are factors associated with PPA, such as the vulnerability theory and lifestyle factors, genetic contributions to all these different presentations, and superaging as a whole. Because if we can learn about successful aging, we can apply those findings to the general population, potentially. We should also move towards earlier and more comprehensive routine cognitive screens in general medical populations in order to try to catch cases of dementia earlier. Finally, it's important to increase awareness in the general public about lifestyle factors contributing to AD to ensure that people are aware of the impact that their choices can make on their future brain health. Thank you all so much for listening to my presentation, and special thanks to my amazing mentor, Rachel, for all of her support and guidance throughout this project.
Thank you, Sophia. Yeah, I believe that your mentor might be here today, just like going through different presentations. I'm sure that she will be very proud as well. Again, if you have any questions, let me know. I actually have 2 questions for you. So you mentioned about super aging, right? And then it's like there's a possibility that being female or having a very extroverted like personality might cause that. I was just curious if you can like elaborate more on like what are some like research or like cool like stats that you found on that.
Sure. Certain studies have linked being female to being a super ager, although it's kind of a topic of debate right now because since women live longer, they're more likely to be a super ager, but women are also more likely to get AD. So it's kind of both sides. And then in terms of the kind of psychosocial factors and being extroverted, those were also found in certain studies that just linked various different factors to super aging. But all of that definitely requires future research to kind of confirm those findings.
I know you had limited time with research, right? So I'm curious if you had extra 2 months, what are some topics that you would focus on to narrow down and like further your research on this?
I honestly would have loved to do a whole project just on super aging alone. I think it's really fascinating, and just kind of broadening and deepening my research into that would be really interesting. And maybe exploring more of the lifestyle and psychosocial factors that you mentioned would be great too.
Got it. Thank you, Sophia. I mentioned that you said your mentor's name is Rachel.
Mm-hmm.
I believe she's listening. I think she also dropped a comment.
Oh, hi, Rachel.
Also, just a huge shout out to all of the mentors who like help our students like guide them through their projects. And then from Ojasvi, we also have a question. Actually, I'm gonna invite Ojasvi to stage right now because he or she is coming up next. So I think it will be great to have that live conversation. Hi, Ojasvi.
Okay, so I was just kind of curious. You did mention like the presentation of Alzheimer's disease is present like super agers, which kind of does change. Could you like elaborate on how like specifically it changes, because that changes like the kind of like the brain's physiology? Because that sounds really interesting. Like how on one end it can actually insulate them from the bad effects of aging, but on the other end, for actual Alzheimer's, it causes cognitive decline. So is there like any do you think you can elaborate a bit?
Sure. Yeah, there you go. So like you said in your question, it's kind of a question of resistance or resilience. And so is it that their brains kind of are resistant to developing AD in the first place? In some cases, that's true. Or in other cases, they weren't resistant to it and they have AD in their brains, but they're maybe just resilient to its effects and can still function normally even with those effects. So that's one big question and debate, but it generally appears to be a combination of the two. And then for the pathology specifically, there are a lot of different changes or things about super agers' brains that are different from normal brains. So I don't know if we have time to get into all of them, but I'd love to talk to you more about that if another time. Or I can send you some more details too if you're interested.
Yeah, sure thing.
Yeah, guys, feel free to like leave your email in the session and have those conversations offline. Great, and thank you, Sophia. All right, I'm gonna remove you so that we can feature Ojasvi, but definitely stay in the room. Hi, Ojasvi. So last but not least, we have Ojasvi, a sophomore from San Jose, South California. Yeah, let me know if you need help with your, setting up presentation. Otherwise, the stage is yours.
Can you guys see my screen?
Yes, that's perfect.
Okay. I'm ready. So, hello, I am Ojasvi Mudda, a high school sophomore. Today, I will be presenting the research I did with my mentor, Ellie, about the expression of complement system genes across the subtypes of glioma, a malignant brain cancer. So today, I will go over the background of my research, the methods, the results, and the discussion. So first off, this is the background of my research. Glioma. Gliomas are a malignant and poorly understood cancer that occurs in the glial cells of the brain and is associated with poor prognosis. It is characterized by high levels of tumor heterogeneity, making treatment difficult. Gliomas are divided up into different subtypes based on clinical factors and mutational signature analysis. First of all, gliomas are divided into two clinically defined subtypes, lower-grade glioma and glioblastoma, which differ in aggressiveness and metastatic stage. Gliomas are also divided into four transcriptional subtypes defined by gene expression: proneural, neural, mesenchymal, and classical. These subtypes vary in histology, survival, and response to intense treatment. Finally, gliomas are also divided into two mutational subtypes based on their IDH mutation status. IDH mutant has the mutation in the IDH gene, where IDH wild type doesn't have the mutation. IDH wild type is associated with a poorer prognosis compared with IDH mutant. I'll now be moving on to the next branch of my research, the complement system. The complement system is a branch of the immune system involved in many critical immune functions, including optimization, inflammation, and the killing of pathogens. The complement system can also be considered a double-edged sword. Recent research has shown it to have a pro-tumor role in maintaining metastasis, immunosuppression, and was associated with a negative impact on treatment. So we wanted to find out whether the difference in outcome between the different subtypes and grades of glioma is correlated with the aberrant expression of complement system gene. I will now go over the methods that I used to answer my research question. RNA-seq data was collected from the TCGA database and compiled into a summarized experiment. To analyze this data, R, a statistical programming language, and bioconductor packages were used in order to perform the analysis. Bioconductor, an open-source repository, has many R packages dedicated towards analysis of genomics data. The packages used for this analysis are the DSIC2 package, which is used for differential gene expression analysis, the feedback package, the FJCA package, and the SAMR package, which is used for outcome analysis. This is the workflow used. So RNA-seq data was transformed to a summarized experiment. DSIC2 analysis followed, and the resultant DSIC2 object was used to produce a heat map with expression values of complement system genes, and was also used to perform gene set enrichment analysis. The summarized experiment is also used to perform outcome analysis correlating expression of complement system genes with prognosis using SAM-seq. Now I'll be presenting the results that I got from DSIC2, heat maps, GSAA, and SAMR. This is the next two slides are the slides with the DSIC2 results. This is the result of the DSIC2 analysis, which produces a MA plot that shows the differential expression of complement system genes across the two subtypes. Overexpressed genes are above the x-axis, and underexpressed genes are below the x-axis. On this slide, the transcriptional subtypes were compared with complement system gene expression for the classical subtype, as the classical subtype is the most similar in presentation to normal gliomas. There were 67 genes differentially expressed across the proneural and classical subtypes, 27 genes differentially expressed across the neural versus classical subtypes, and 107 genes differentially expressed across the mesenchymal subtype. On this slide, complement system gene expression was compared across IDH wild type versus IDH mutant in the two clinical subtypes of glioma, lower-grade glioma and glioblastoma. In low-grade glioma, 33 genes were differentially expressed, while in glioblastoma, 21 genes were differentially expressed. The following two slides show the heat map generated with the gene expression data from the DSIC2 package. Hierarchical clustering was performed based on the sample similarity. The heat map was then annotated with IDH mutation status, transcriptome subtype, survival in months, vital status, and Karnofsky performance score to determine if the expression of complement system genes are a supervising factor for glioma subtypes. In glioblastoma, clustering is observed with the transcriptional subtypes of 3 clusters. a proneural cluster, a classical cluster, and a mesenchymal cluster. The heat map generated for lower grade glioma also shows clustering with the transcriptional subtypes with 3 clusters. The proneural cluster, the classical cluster, and the mesenchymal cluster. This analysis shows that the expression of complement system genes partially supervises the clustering of glioma samples, which further supports our analysis. GSEA analysis was performed to create a pathway enrichment graph comparing enrichment in the complement system pathway across the different subtypes. Overall, the complement system was the 11th most enriched pathway in both low-grade glioma and glioblastoma. This slide shows the pathway enrichment across the transcriptional subtypes in glioblastoma with an overall positive enrichment. The mesenchymal subtype is noted to have the most enrichment out of the subtypes. These graphs compare the enrichment across IDH mutant versus wild type in both glioblastoma and low-grade glioma. There is negative enrichment across IDH mutant versus wild type in both clinical subtypes. SAM-seq analysis was then performed, which generated the complement system genes associated with worse prognosis. Overall, in glioblastoma, 25 genes were associated with worse prognosis. Across the transcriptional subtypes, 27 genes were associated with worse prognosis in the proneural, 15 genes were associated with worse prognosis in neural, 4 genes were associated with a better prognosis in mesenchymal, and in the classical subtype, 22 genes were associated with a better prognosis. Analysis across the IDH mutational subtypes in glioblastoma are shown. In IDH wild type and mutant, 62 genes were associated with worse prognosis. In low-grade glioma overall, 55 genes were associated with worse prognosis. Analysis across the IDH mutational subtypes in low-grade glioma are shown below. In IDH wild type, 76 genes were associated with worse prognosis compared with IDH mutant, where only 18 genes were associated with worse prognosis. Overall, complement system genes are differentially expressed across subtypes and can be associated with poor prognosis. The expression varies across the subtypes. The proneural subtype had the most genes associated with poor prognosis, while the mesenchymal subtype had the most genes differentially expressed overall with the highest pathway enrichment score, but with the less clear correlation with outcome. This could potentially indicate a correlation between complement system gene expression and the proneural mesenchymal transition associated with recurrency, metastasis, and poor prognosis in gliomas. In the mutational subtypes, IDH wild type overall have the most expression of complement system genes versus the mutant. Discussion. Here are the implications from my research. This suggests that aberrant complement system gene expression can be associated with the varying phenotypes, prognosis, and reactions to aggressive treatment amongst the different subtypes of glioma. This can also lead to further insights on interactions between the complement system and tumor metastasis, which can lead to possible actionable targets for treatments. Further research can investigate the potential link between the complement system and metastasis. Wet lab research can also be conducted targeting specific complement system genes to determine potential actionable treatment targets. I would like to thank my mentor, Ellie, for her support and guidance throughout this project. And I would also like to thank Polygence for giving me this opportunity to conduct research. Here are my references. And thank you all for attending this presentation. I hope you enjoyed it. I'm now open for questions.
Ojasvi, great job. Like Elizabeth said from the comment, like super proud of what you accomplished. 2 questions for you. So first is like, what got you interested in this topic in the beginning?
Well, I was always kind of interested with cancer, just due to like experiences within my family with cancer. But what specifically spurred my interest in gliomas and the complement system was actually a prior research experience I had with a team of high schoolers where we investigated the interaction between gliomas and the complement system and using that as an actionable treatment. So I kind of wanted to expand in that research further and to see if there's any inherent differences in gene expression, and to like further like categorize it based on the subtypes, which are known for having like different prognoses, different histology, different reactions to treatment, and to see if there's any more correlation. So it was kind of spurred by my initial exposure to the complex AMS.
Got it. That makes sense. And also a reminder to our audience, make sure that you type in the session chat box instead of the event one, so that Ojasvi can see it, especially when we are giving, your thank yous, appreciations. I want to make sure that each of our presenters get to see it. Finlay asked, what was the most surprising fact you learned in your research?
Well, the most surprising fact in general I learned in my research is just how something like the complement system, an immune pathway which is designed to help protect our bodies from infection, can sometimes be kind of co-opted into harming the body and increasing cancer metastasis. It's kind of a general theme that is not only seen in my research, but in general medicine. For example, like in COVID-19, like cytokine storms which overload the lungs. So I just found that was just that stood out to me overall.
That makes sense. We also have a question from Jitendra. I'm sorry if I'm like totally butchering your name. She or he asked, what are your plans to take this further?
So if I could take this further, I'd love to investigate the reaction between the connection between metastasis and the complement system, which has been a bit suggested by my research and also by other review papers. I'd like to kind of take it in further. I'd also like to, if it's possible, do some wet lab experiments, which can further kind of confirm my research. And I'd also like to expand it to other cancers and see whether they also have similar or different patterns of complement system gene expression and malignancy.
Got it. Thank you so much, Ojasvi. That was excellent.
Thank you. Thank you for this opportunity.
Thank you. Yes. So again, thank you, everyone. Thank you so much to all of the presenters today for all of your hard work on your projects. And a huge thank you to all of the audience members for coming to support student presentations. We at Polygence are incredibly proud of all of your achievements. And we're so glad that we got to cheer you on and celebrate you on stage today. We would like to encourage you to attend and support other student presentations throughout the rest of the day. And you can simply navigate back to the reception area and click on the other sessions. And also a quick reminder, there's also a college panel going on right now, talking about how you can talk about your Polygence projects in your college application if you're interested. Again, thank you so much. And I'll stay for 2 minutes for any other questions.